Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So welcome to MSR Cambridge, those who have come from across the road. Gives me great pleasure to introduce Mike Hicks, who was a visiting researcher here some years ago.
2008, yeah.
2008, wow.
Gosh.
2008 is not that long ago.
That's shocking. It's great to have Mike back. He's gone on to great things. He had been at University of Maryland. He's now the director of the Maryland Cybersecurity Center, professor there, leader of the Plum Group, and he's going to be speaking about this topic, dynamic enforcement of knowledge-based security policies. Mike Hicks.
Thank you very much. Glad to be here. So my research generally is about programming languages, and I've worked on many different topics, some listed up there. I list these in case any of you are interested in talking about them with me later today. Today I'm going to be focusing on privacy-preserving computation, and the context of the talk is free sites. So the thing that's nice about Facebook or MySpace or LinkedIn is it gives you a way of using a free service to connect with friends and colleagues. It's easily accessible and so on. Maybe the bad part is that the service is not really free. It's being paid for by free use of the company of your personal information, say for targeted advertising. So many proposals have been put forth to try to rectify this problem of avoiding the third party holding your data. So one example is actually it should be PRPL, not PRPI, that came out of Monica Lamb's group at Stanford, and the idea there is to have a more decentralized approach where data is stored on separate sort of agnostic servers and users can talk to each other individually rather than through a central site. Persona is work that was done also at Maryland that takes the PRPL model one step further and encrypts the data that's stored on these storage servers, and then only those with attribute keys are able to decrypt them. So all of this is fine, but ultimately it's limited, we think, by the use of access control as the policy. You have to decide once and for all whether someone can see this data or not see it, as opposed to having more specialized release. So just to illustrate what I mean, let's look at the status quo with Facebook. Right now what will happen is some advertiser will present some query, some specification of the demographic they'd like their ad presented to. They give that to Facebook, and then when I log into Facebook, I see the page that I'm looking at, but also ads. And I may see, for example, this photography company's ad if I match the query that they sent to Facebook. Now, the alternative strategy could be something like, well, now the photography company will send their query to Facebook, and then the query can be sent to you, and you can run the query locally and then return back to Facebook whether or not you displayed or clicked on the ad. And then that way Facebook can be paid for having presented this ad, but at the same time you get to hold your data locally to run the query, so Facebook doesn't have to own it anymore. And this idea has been proposed, for example, by the PrivAd system that came out of MPI. Yeah?
Sorry, how do you make sure that someone is not abusing the system? Now, if it's running on the computer, then I can just send queries and
answer the wrong queries and so on?
Lambdax.no.
Sorry?
Lambdax.no.
So you could do that, and you can do that now. You already have this problem, right? You have ad blockers and things like this, and so it's really no different, I would claim. You can already lie about your data. People already do that. The idea is that it's in your interests to answer truthfully, as long as answering truthfully does not compromise your privacy, because then you'll see ads that you care about rather than ads that you don't, and you can always just block the ads if you don't care to see ads. Okay, so let's, for the purposes of discussion, remove Facebook from the picture and just imagine you're interacting with an advertiser directly, and then we can step back and answer a broader question of, let's suppose that you're the curator of your own data, and now people, instead of just taking your data and doing whatever they want with it, they send queries to you to ask to have access to the data in some way, and the problem that's put to you is, should I answer this query or not? Is there at some point, am I going to be revealing too much information in answering the query, whether that query comes from an advertiser or anybody else? Okay, so as an example, let's suppose for this photography company, the query is, well, are you female, engaged, and young? because if so, I would like to shoot the photos for your wedding. So maybe that's fine. That doesn't uniquely identify you. There are many young women who are engaged. On the other hand, if they asked you for your, that's a typo, that should be gender rather than age. If they asked you for your gender, zip code, and birth date, then in the United States, this would uniquely identify you 63% of the time. So that would be information you would not want to respond to in that particular query. So the question is, how can I tell the difference between the queries that are going to ask for very little information, maybe a little bit more information, and then maybe a lot of information? How do I decide whether to, how much information is revealed by my query to decide whether to answer it or not? So the approach that we take is to maintain a representation of the querier's belief about possible values. So just as you would have an access control policy for different people that would interact with your data, you will likewise have a belief representation that represents what you think they know about your data. So with the example of Facebook, you can start off with demographic information about Facebook users so that knowing nothing else, Facebook is likely to think that you're young and you're male some percent of the time less than female and so on to set this initial belief. Okay, so then at that point, when the person that you've set this policy for starts asking you questions, you can decide by whether or not the question would reveal too much about your information by revising this belief. So we start off with this representation, we depict it as a brain, and we write it as a probability. We represent it as a probability distribution. So it's the likelihood of each of these values being some amount. How likely you're male, how likely you're female, what your likely birth year is, and so on. Okay, so then the query shows up, and you evaluate that query with respect to this belief representation, and you get a revised belief that you can use Bayesian reasoning to produce, and you can then decide, has this revealed too much information? If the answer is no, then you can answer the query, and now you use the revised representation for the subsequent query. If the next query comes in, say it's that second query that asked for too much information, then you can reject that query, retain the representation from before, answer the next one, and so on. So that's the basic idea of the system that we're developing.
So if each query made only a very tiny difference, but they kept asking you queries, that could make a big difference.
Yes, and so that's why we maintain the representation with each query, so that over time, as the knowledge accumulates, eventually you'll say, no, I'm not going to answer anymore.
This is the straw that broke the camel's back.
Yes, that's exactly right.
I'm not going to tell you any more, even though it really doesn't tell you anything much new.
That's correct.
Okay.
So you, as the queried person, have a representation of the querier's knowledge of the world.
That's correct.
And you make decisions, informed decisions, according to what you think he thinks.
That's correct.
But what he thinks could be different than what
That's true.
You think he thinks.
Yes.
Yes, so this is a big assumption that we're making in this work. So I think for systems like these large online social networks, there are many contexts where you can come up with a reasonable estimate of what the other person believes about you so that you can make decisions. And I guess the other thing to say is that you want to compare this against the status quo, which is you just give them everything and you just trust by some legal privacy policy that they don't do the wrong thing. The other point is you can also use a system like this, as I'll point it out a little bit later, to not necessarily enforce policies where you reject queries, but instead you just track information that has been released. And in that case, you can always use sort of the entropy of the query with respect to the prior queries to represent how many sort of bits of information have been released, right? So for in particular, you can always set the initial belief to be the uniform distribution, that it could be one of any possible number of things, and then each query, that's going to conservatively maximize the amount of information that's communicated when you respond to queries, and you can just keep track over time of how much information is being released, and then decide retroactively to say, hey, I just had this big privacy breach with all these people I was interacting with, to whom did I release too much information, and then you could use that to audit the result. So then in that case, your initial estimation is not so important. I guess I'll say one other thing, which is you don't have to maintain just one belief. This is not work that we've spent a whole lot of time thinking about. You can maintain multiple beliefs if you think instead of one probability distribution, they have one of many possible beliefs. Our representation for beliefs actually allows you to do that, to say, to represent many possible distributions, and then you just do this whole process on all the distributions instead. Okay, so the contributions of this work are first this idea of knowledge-based policies where you maintain a belief and you answer or do not answer a query based on how much information you believe the adversary is gaining. And then the second is we implemented this idea using a new kind of probabilistic interpretation, executing of probabilistic programs based on abstract interpretation. So basically we define a method that you can think of as a functor that takes a regular abstract domain and turns it into a probabilistic abstract domain so that we can do the belief revision and everything else that I was just talking about. So those are the two main contributions of the work. At the end of the talk, if I have time, I'll talk about an extension of this work beyond this sort of Facebook context to working with multiple parties who are all participating in some computation where they each present secrets, rather than in this case where only one person has a secret and the other person has a query. Okay, so let's step through how the technique works. So here's Bob. Bob was born on September 24th, 1980, and that's represented there at the top in terms of B day and B year. And we're going to represent the adversary's belief as this uniform distribution that his birthday is between 0 and 364. It could be any day of the year. And his birth year is 1956 to 1992. So we could represent any distribution we want. I'm just using the simple one to make the exposition easier. Okay, so now let's suppose that Cakes.com sends Bob a query that says, if this week is your birthday, I want to provide you a special offer. So it asks whether today being the day 260, if Bob's birthday is this week. If so, it returns 1 saying show him the ad, otherwise don't show him the ad. So we can see at the top there, Bob's actual birthday is the little orange square, and the answer of the query is not, Bob's birthday is not this week, and so we're going to actually produce 0. Running the query would answer with 0. Now, revising the belief of Cakes.com, we would get this distribution that's shown at the bottom, right? Bob's birthday is not this week, so we slice out this week as the possible birthday, where the x-axis is birthday and the y-axis is birth year. So the question is that okay? Is that revealing too much information or not? Okay, so the way we define okay is we use what we call a knowledge threshold, and intuitively speaking, I'm going to refine this in a minute, we want the probability that the adversary ascribes to my secret to be less than a threshold that we call the knowledge threshold. So, and the choice of t depends on the risk you ascribe to revelation of your secret. So in this particular case, let's suppose that Bob sets his threshold to 1/5 for his birthday. I want you to not know me within a 1 in 5 chance for the day of the year, and then the particular combination of birthday and birth year together as 1 in 20. Okay, so why would we do that? Why not have policies for each one of them? Well, it's because when you have these tupled policies, it gives you the opportunity to allow the querier a bit more utility, right? So what this is saying is that I'm okay with you knowing either my birthday or my birth year to some fine degree, as long as you don't know the other one, because in knowing both, you're going to know more that would be able to uniquely identify me. And I'm going to put some limit on birthday to never be better than 1 in 5, but you could learn up to that amount as long as you don't learn too much about the birth year or vice versa. Okay, so you have a little more flexibility there. So right now, currently, the probability of the birthday is 1 in 365, and the probability of the pair of them is 1 in 365 times 37. Both of those are clearly less than the thresholds, and so we're good. Now, after the query, the revised belief looks like this on the bottom, and so should we answer the query? And the answer is yes, because they are within the threshold. The birthday is now 1 in 358 because we carved out this 1 week, and the pair of the two of them is clearly a whole lot less than 1 in 20, and so everything is fine, and we answer the question.
So you're taking the probability of him knowing your exact birthday, right?
That's correct.
So him knowing your precise secret. Well, would it make a difference if you cared about him not knowing that your birthday was in November, so sort of some region, right? Because you're saying provided he doesn't have a very
yes.
So
there's
a sort of
yes, so you could do that. So you could basically define a tuple in some sense is a special case of a more general predicate that you could define over your secret, that you want the certainty of this predicate, of the answer of this predicate being less than a certain threshold. So you could easily extend it to do that.
You just want a measurable set. I mean, you can think of the birthday as just a set of a single element.
Yeah.
And you can have another secret which is a measurable set, subset of your...
Right, so you can use the predicate and you could run it on the probability distribution, which would then give you a probability of the answer of that, and you could say that that needs to be less than the threshold. Okay, so now let's go to the next day. So the next day is day 261, and then cakes.com asks the same question. And this time, now we are within the week of Bob's birthday, and so we're going to get the answer as 1 instead of 0. And then after belief revision, we're going to get that revised belief at the bottom. Okay, so that's bad, because now the probability that the adversary knows the birthday is 1, so we ought to reject the query. Okay, but does anyone see the problem? From the querier's perspective, let's assume that the querier knows my policy. He knows that my threshold is 1 in 5. Or in fact is any reasonable threshold, right? Any threshold that's not 1, then the querier is going to know that the only reason that I would reject is if 267 is my birthday. Okay, so I backed myself into a corner because rejection now, I can't, once they've asked the wrong question, I'm stuck. So the problem is that, this is sort of obvious once you think about it, the problem is that my decision about whether to accept or reject, the definition of my security policy depends on my secret. So whether I accept or not reveals potentially information about my secret, and in this case it reveals far too much. So what we want is we want the decision to accept or reject to be independent of the actual secret, and therefore that decision won't ever leak any information. So we can do it this way. We can say, for every possible output O and every possible birthday B, it needs to be less than the threshold. And if that's true, I'll accept, otherwise I won't. In other words, if there exists a birthday, whether it's my birthday or not, such that rejection would reveal too much, such that answering would reveal too much, then we reject. So the idea then is that even if Bob's birthday is not 267, let's say it's some other place over here, we're still going to reject this second query because there exists a birthday that would back us into a corner. So this methodology where you make the security policy independent of the secret is called simulatable auditing. It's a way that the adversary, knowing what our representation of his belief is and our threshold, knows whether or not the query is going to be answered. He doesn't even need to send us the query at all. He'll know whether it's going to be answered or not. And so therefore it can't possibly leak any information about our secret if he can do it himself. So,
question?
Yeah.
Did you consider a probabilistic approach, like where you would toss a coin, as well as looking at the whether you're revealing information, so that sometimes you reject queries anyway. So
you could do that. I think I'm going to have an example later on that shows how that would work. So for this particular example, the first query we're always going to accept, no matter what your birthday is, you'll always accept because it will always be within the policy. The second query you'll always reject, no matter what your birthday is, because there exists a birthday that's in bad shape. And then it turns out that the third query, given that we accepted and rejected the first two, we will actually accept once we get to day 266. And you can again do a calculation that says, well, if your birthday, whether it's 0 or 1, you'll never do better than knowing 1 in 5 or 1 in 353, depending on what your birthday is. Okay. So, so we implement this by using an abstract interpretation methodology. The idea is that we could use really any probabilistic computation approach. So the way that we implement these queries is we run the query using the belief. So we basically, instead of having the program be a function from states to states, which is the way it's been looking, the way I've been writing it here, you can think of this little program. All of these global variables are referring to a state. And so at the end of the program, the state, whether out is 1 or 0, is the result that we're using. So it's from states to states. And so what we want to do is we want to run it over distributions of states rather than regular states. And the simplest way you can think of to do that is to actually try every possible state, right? So I could basically run my program. Actually, I think I could do this, right? I could take the program and I could sample every possible input state and run it and produce the output state. And do that enough times that I'm able to figure out what the output distribution is from the input distribution. And if I want to have perfect clarity about what the output distribution is, I need to actually sample all of the states, at least up to the point of being able to make a sound decision about the threshold. Okay, so that would be slow. right? Is that because it's now a function of the size of the state space. So instead, what we do is we avoid this because sampling-based interpretation is going to be too slow, and so we developed an abstract interpretation methodology that allows us to have a more compressed or more compact representation of distributions to make things more efficient. So I'm going to show you how that works. Okay, so our abstract domain is going to be what we call probabilistic polyhedra. So polyhedra is a normal abstract domain. It's quite common. And what we do is we add probabilities to this domain. So the idea is you're going to represent a probabilistic polyhedra as a bunch of linear constraints that describe this shape. And then you're going to add to it a measure of the probability of each point. We're interpreting this discretely. Every state is, we're only considering discrete distributions. So every point inside of this space has this probability. Okay, so this is the simplest representation you could imagine of a probabilistic polyhedra. The probability of each point and inside the shape and the definition of the shape. And then what happens is after we...
Probability outside is 0.
That's correct. That's right. So as we're doing our execution and our belief revision and so on, we're going to end up getting, states that look like this, where here we now have 3 probabilistic polyhedra, and the points, the ones inside of here have a certain probability, the ones in here have a certain probability, represented by these numbers down here. Okay, so that's the basic idea, is the polygon C and the probability per point.
So Mark, I was kind of expecting to see something more distribution-like, the belief about, my birthday might be initially uniform and gradually becomes more humpy.
Yeah, so it will.
But this is very discrete. This is, uniform within the polygon and 0 outside. So it's a kind of like a...
Oh, sure, fair enough. So, so if you start off... So you can certainly start off with a non-uniform distribution, and then as you perform belief revision, you're going to basically be slicing off parts of that distribution, right? The point is that the adversary is gaining more and more knowledge about you. And so if you don't have any coin flips inside of your programs, if your programs look like the programs I just showed you, all you're going to be doing is making that distribution smaller and smaller by slicing points off, not changing the probabilities of any point. Now, once you add coin flips to your language, then you add uncertainty.
Once you add what?
Coin flips.
Oh.
Once you add probabilistic choice to your language, then you will start introducing more humpy distributions, and I'll show you what that looks like in a minute. Because we do.
At the beginning of that sentence, you said there's nothing to stop you having non-uniform distributions, but this can't describe non-uniform distributions.
Sure, can. You can just make a. They're always discrete, but you can make it so that each polygon has different, so that the total probabilities.
Lots of little polygons.
Yeah, lots of little polygons, right? That's what this is.
Okay.
Right, and they can each have different probability mass that then makes this one more likely than this one, than this one, than this one.
Very different to a Gaussian distribution, say, isn't it? The sort of single number that describes a...
Yeah, so we have a discrete representation of this single number that represents this.
Okay.
I guess I haven't really thought very much about you could take advantage of representing things more compactly in that way. Okay, so we could just stop there and have these representations, many polygons, but actually that would be inefficient. That over time, as I was saying, you're going to be slicing up this space quite a lot, and you'll generate many, many polygons, and it'll become more and more expensive to perform the computation. So we need some way of doing abstraction. So what we do is we allow collapsing regions so that what was 2 polygons can now be contained in 1 polygon. But now we have to change our representation because before, implicitly, every point within the polygon was in play. Every possible point had the same probability, whereas now that's no longer true. It now may be that when I draw a box around 2 regions that were there before, some points are more likely than other points. So this is just to illustrate how we might end up with too many regions. It's going to happen with disjuncts. So here, this is the state that we were in after that first query that I just showed when we sliced out the week. And now let's suppose that this crazy guy here sends us this query that says, well, if you have a decade year, if your birthday this year is going to make you 20 or 30 or 40 or 50 or 60, then return true or else false. And on returning true, I guess, returning false in this case, we're going to end up having this as our representation, right? Because we sliced out all of those possible decades. Okay, so then that's why we're going to want to do the subtraction. So here's the representation that we would have had if we had every possible one. And now here we could go back to a more compact representation where we draw a box around both of those sets of polygons. But then what we need to do is we need to put a bound on the total size of the number of points inside the polygon. So the complete area of this polygon would be 9620. But because actually a bunch of the lines in here are missing, we're going to bound the size as 8580 to say that this represents all distributions that have points in this space such that there are only 8580 points. Okay? So this is an abstraction. This abstraction represents this distribution, but it also represents a bunch of other distributions that are going to cause us to behave conservatively.
Yep. So this is not the first abstraction that came to my mind when I saw this.
Okay.
And I'm wondering why you didn't choose the first abstraction, which is you just take the boundary rectangle and you renormalize everything so that the sums would be the same. So you actually renormalize P, and you say that, oh, I'm over-approximating the probability of some value inside that rectangle. Would that work or not?
So we're going to get to that. So maybe I chose the wrong pedagogical approach to get to closer to the one that you're thinking of. So why don't we get to the end, and then we can have this conversation again. Okay, so this is just illustrating that this represents multiple distributions. Okay, so another thing that can happen, so now this goes to your question, Andy, and also to Simon about the probability of points being different. In our language, we permit coin flips. So what this says is we're going to do the same query as before, but then 1 time out of 10, we're just going to set output to true. Okay, so P if takes a rational number, some number between 0 and 1, and then it has a biased coin flip to that amount with that probability. Okay, so then what's going to happen is...
In the query, right?
This is in the query, yes.
So why would the querier want to do this?
Okay,
Perhaps
so...
to make you more likely to say yes. Is that...
Yes.
I mean, because it gives him less information.
That's right, but
So
otherwise you'll just say no.
I see. So he's messing up his own query.
Correct.
In order to persuade you to be nice to him.
That's right. But another way to look at it is, in some ways we don't care whether we add the noise or the querier adds the noise. But if we add the noise, probably to make it worth our while, so that the utility would be worthwhile, we would want to tell the querier that we added noise to the query. So I think you could go with either argument. I like it better that the querier adds his own noise, because then he knows how to account for the noise. So in fact, I'll just digress for a moment. Our approach is aiming to avoid trusted third parties, right? We want to get rid of Facebook, and everybody has their own data. Okay, so there's this other approach to privacy that I'm sure you've heard of called differential privacy, which looks at privacy of databases, i.e. a trusted third party. And so you send queries to this database, they add noise to the result, and they send you the result back. I'm saying let's avoid third parties altogether. Let's everybody have their own data. But now the question is, if you have that scenario, how can you produce aggregates? Because asking each individual for their record in the database is going to violate their personal privacy policy, right? If I wanted to compute the average salary in the department, how do I do it without asking each one of you for your salary, which is going to violate your privacy policy? So the answer is you can do it by adding random coin flips to it. There's a technique called randomized response where you say, what is your salary? Flip a coin. If it comes out heads, tell me the truth. If it comes out tails, then do several other coin flips to perturb the actual number. So I never respond to you with certainty as to what my actual salary is, and because you know how I did the coin flips, you can account for that when performing the aggregate. So people develop this as a survey technique to ask sensitive questions like, are you having an affair? Are you, I don't know, stealing from the company, whatever it might be, so that people will answer truthfully. So you could actually do the same thing, and that would be a reason for why the adversary might insert their own coin flips. Okay, so anyway, here we are. We now have these regions that have different probability points in them, right? The reason that you would say true is very likely because it is your birth year or whatever, but there is some chance that in these gaps that those are also possible because you said true because of the coin flip. So in this case, we need to extend our definition of region. So here you go. Here's your bound on probability because the probability of points could differ inside. Okay, so it turns out that we need to do even more than that. So we end up we bound 3 additional properties of the regions. One is we bound the probability of each point. We bound the total size, the total number of points in the region, and we also bound the total probability mass within the region. So this is redundant. You don't need to do this. Just the first 2 are sufficient for having a reasonable abstraction. But it turns out that by doing this, we can get more precision. That there are times when some operations that you want to perform that maintaining the probability mass is easier and more precise than just the probability times the size. So we maintain all of these as upper bounds and also as lower bounds. And the reason is that when we do conditioning, so that the case when I ran the query and I said, oh, in the case that output is 1, I need to divide the probability distribution. And in order to soundly approximate what the adversary's belief is, I need to under-approximate the distribution that I'm dividing by, or else I'll under-approximate what the adversary knows. So I need to maintain upper and lower bounds in both cases. And in fact, well, there's several aspects of this representation that are novel, but this is the most important difference between prior work on probabilistic abstract interpretation and what we're doing, is that none of them consider conditioning or observations. Okay, so just to give you a sense of how the abstract interpretation works, so it's all kinds of, if you were to look at our paper, you would see all of this math and geometry about computing. When you add 2 probabilistic polyhedra together and you draw a bounding box around them, what is the new size? What's the new probability mass? So here's an example. If we were to add P1 and P2 to get P3, how would we compute P3? Well, first we'd have to compute the convex hull of C1 and C2, that is those shapes. We'd have to merge them together and make the result convex. And then we would ask, okay, well, what's the smallest possible and the greatest possible overlap? Because remember, not every point in those 2 shapes is necessarily in play. So we look at the most optimistic overlap and the most pessimistic overlap. We also look based on whether overlap is possible, how that's going to affect the probability of the points. For example, if you completely overlapped, then basically you're going to add the minimum probabilities together for those 2 points. You're just going to double the probability mass. But if there's only partial overlap, then you can't do that, and you have to maintain sort of the least lower bound of the one side or the other, and so on. You just make all of you have to just put your thinking cap on and work through all of this geometry, and then do your soundness proof to make sure that you got it right.
Where is this S used? Where was it actually used? The number of points inside the.
When is the size used?
Yes.
Let me think about that.
I can see what the probability bounds are used.
So it's used in projection. So when you do an assignment in your language, so you say x equals something, what you'll end up doing is you'll have some representation for x in your shape. And if you have a non-invertible assignment, so the right-hand side doesn't mention x at all, you're going to collapse everything you know about x, right? So you're going to have some shape, and you have this x-axis, and you're going to smush everything this way. And you need to know how many points you just compressed onto this one axis from the axis that you got rid of, in order to boost the probability per point in the projected amount. So that's where the size comes in. And basically what we do is we end up computing, we use the size and we also look at the shape to figure out what's the maximum and the minimum sort of extent of the axis that we're compressing. And we use that to set the new probabilities in that place. Okay, so the biggest, mostly we're able to do, most of this is simple arithmetic and using existing abstract interpretation libraries. So we use something called Parma to do all of the polyhedral operations like the convex hull. The other thing we have to do is counting. We have to look, well, how many points are inside of this space? What's the minimum and maximum extent and so on? And so we use a tool called LattE that does this geometric counting for us. It turns out that LattE is not very good software. Like it's buggy and it crashes and it's really slow and well, I'll say more about that later.
So it's just about maximum and minimum overlap. These are abstractions, right?
Yes.
So all you know is that there are these 2 polyhedra that kind of visibly overlap, and then you imagine that all the points were as far out of the overlap as possible. I see. So you know nothing about the internal structure.
Correct.
Because it's an abstraction.
Exactly.
I see. So that's why you say it's really just simple arithmetic. Okay.
Right. So this is an illustration of what's going on with this. So this is sort of the concrete representation of these 2 distributions, and when you overlap them, intuitively these points are now more likely than these points because you've added the 2 distributions together. So what will happen if you have a probabilistic polyhedral representation of this? So here's C1 and here's C2, and the size of these things, if every point was represented, is 140. But let's suppose, for example, that while every point in C1 is represented, in C2, we're only going to, only 30 points are in play. So in this case, the total number of points is going to be 130. We're just going to add them together in the maximal case, right? If there's no overlap between them, and then yeah. So then this just shows where the intersection is. Could be 20 around here, and so then that's going to cause us to change the maximum to 120. Yeah, so what this is saying is that if I stupidly just added these 2 points together, these two things together, it would be sound for me to say the maximum is 130, but that would be imprecise because there's no way with these two shapes, given these two shapes, would ever have more than 120 points, and so that's one place where we can change the size to be 120. Okay, so the main thing to take away from this slide that I haven't already talked about is that polyhedra are just a most expressive kind of shape that you could use for representation. There are other shapes that are cheaper to represent but lose precision. So these are intervals where you have no relations at all between axes. You just have lower and upper bounds on variables. And octagons, which have this representation, you can only have a relation between two variables. That's a linear relationship. So it turns out that octagons are really useful in practice. I just came from ENS, and they never use polyhedra. They only use octagons. So anyway, sure enough, octagons are a fine representation to use, although in our case, actually, intervals turns out to be really good too. Okay, so we did a bunch of experiments. So I've already shown you a bunch of these, the birthday query, the second-day birthday query, and then the special query that slices out the decade years. And then we had several other queries that we all got from Facebook. So this photo and travel one come from examples on the Facebook webpage of what advertisers would write. And this pizza one was, of course, college students want to know where the closest pizza joint is. So if you live within some distance and you're a college student, tell me all the pizza, show me the ad for this pizza location. Okay, so I'm going to show you two graphs. The first one just shows you something that should be intuitively obvious, which is that if you were to implement this by enumeration, if you were to do the silly thing that I showed you in the beginning of sampling all the points and running it all, that's going to be slow. So this y-axis shows the belief that you would have, right? So when I'm going to do the threshold query check, I'm going to see does the adversary's probability, is it less than my threshold? And the more I sample, the more certain I can be about the belief, right? If I only sample 1/3 of all of the points in the distribution, then I have to conservatively assume that the other 2/3 are going to go against me, and the belief is going to be much higher. And so you see that's what's happening here, that over time, as the sampling approach works, it goes better and better until finally it hits the best possible precision here by sampling the entire space after 17 seconds. Whereas when we use probabilistic polyhedra, all of these little these shapes here represent a bound on the number of probabilistic polyhedra that we will allow, right? Until we have to start coalescing them and abstracting. So if the bound is 1, we're here. And if the bound is, I think, 35, then we're here to the right. So what this is showing is that whatever the bound is, we get maximal precision on just with one polyhedron in this particular case. And it will take upwards of 4 seconds to compute compared to 16 seconds. Now, the interesting thing is, here is the same query, but now we'll change the state space so that the birthday is between 1910 and 2010 rather than 56 and 92. So we just made the state space a whole lot bigger. So basically, it's going to take the same amount of time for our abstraction because it's just, it's just as easy to count it. Whereas sampling is, it basically, the program crashed after 36 seconds of doing sampling, right? So this just shows the limitation of a sampling-based approach. Okay, so this graph is showing the precision performance trade-off of the 3 different shape representations, either polyhedra, octagons, or intervals. So this is intervals, this is octagons, this is polyhedra. And the y-axis is the time that it takes to perform the query, and the x-axis is the number of shapes that you're allowed. So the intuition is, as you move to the right, you'll get better precision, but your performance will get worse. So you can basically see this upward trend of performance getting worse as we have more and more shapes. So this motivates the abstraction in the first place. The size of the shapes here represents the precision. So a dot represents the best possible precision, and a big box represents a bad precision. I think there's maybe 4 different possibilities that we discretized it for the purposes of the graph. And then these things are showing, these are the median of several runs, and this is showing the semi-interquartile range between them. Okay, so the takeaway is basically, if you have a small number of polyhedra, so this is with the sequence of 3 queries, then you have lousy precision, but then you get really lucky here at 3. You get the best possible precision, and in all 3 cases, these little dots, and pretty good performance. But then things start to get worse again, and then finally they get better here at the end when there's no bound. So I'll say something about why that is later. This graph at the bottom is just zooming in on this part of this graph to show the precise difference with intervals, that you can see the upward trend again here, but the running times are much better, right? They're all less than a second. And we still get the best possible precision. Okay, so then this is basically the running times for all these different approaches, and you can see intervals do the best. Why is that? It's counting. Okay, so LattE is the reason. What this graph shows is that as the number of constraints that represent your shape increases, the time, this is an exponential, a logarithmic scale, the time is super exponential. Okay, so you just get killed with counting if you have really complicated shapes. And so so it makes sense then why, when you use intervals, you don't have this problem anymore, because counting is a piece of cake when all you have is boxes, right? You have squares or 3-dimensional, 4-dimensional, 5-dimensional boxes. It's a piece of cake to count how many points go in there. And so that's why intervals are really, really fast. Octagons should be a little bit faster, but it seems that LattE doesn't take advantage of the simpler constraints, and so it's not that much faster. We tried to develop our own counting procedure for octagons, but couldn't get something that worked in every case, and so we eventually abandoned it. Okay, so the last thing that I'll say is we noticed this trend where the precision fluctuates here. Why is that? It turns out that the reason is that the order that you choose to merge the polygons while you're executing your program, right? So you hit an if statement, you split, you do the then branch and the else branch. Each of those gets to say 10 polygons. You merge together. So now you have 10 polygons that you have to, on each side, that you have to merge down to 10 polygons to maintain your bound. Well, how do you do that? Well, basically you just pointwise add together those polygons, but you have many choices about which pairs to add when you merge them together. It will always be sound, but it turns out it will hurt your precision, right? So if you have 2 polygons that are largely overlapping and you add them together, you'll lose very little precision. But if they're all the way over here and you draw this big box around them, you're going to lose a lot of precision that way. So what this shows is that when you have only 1 polygon, there's no choices, and your precision is complete crap. So this is this is the best possible belief is here toward the bottom, and then this is the number of, this is the bound for using intervals. The box is the median, and the lower and upper bounds are how bad or good you could get in terms of precision. So what this shows is that for all the experiments that I showed before, the things that were on the plot were these medians. And for each of the bounds. And what this is showing is that if you tried some other combination of merging them together, you could get dramatically different precision, right? So for example, in this case, the median with 3 is really terrible, but you could get really lucky and make it all the way down here to the bottom. So the merging order really, really matters. And the difficulty is coming up with a good heuristic to decide how to merge. Because if you could do something very complicated to compute, hey, this is a good idea to merge, but then of course you hurt yourself because you spent all this time figuring out whether to merge and you ought to just do it. So my understanding is that this is sort of an open problem, a black art kind of problem in abstract interpretation generally, and we just make it worse because of the counting and everything else that goes on top of it. Okay, so I'm going to spend just 5 minutes talking about how we could generalize this idea to multiple parties. And I won't tell you any of the details, and I'll refer you to this PLAS paper if you care to look at them. So we were interested in, again, in this worldview of decentralized computation of, say, people with mobile phones or something wanting to compute answers like, for example, are you and I at the same location? Okay? I don't want to reveal to you where I am. I just want to know if you happen to be sitting in the same restaurant as me. Okay, so how can I do that? Well, I could do this. So the query here could be, are we at the same location? Or a classic example for secure multi-party computation is the millionaire's problem, where these 2 martini sippers are trying to decide who's richer without telling the other person what their actual net worth is. So one thing we could do is we could get a trusted third party to answer this question, right? We could go to, I don't know, Abraham Lincoln and say, can you please tell us, I'll give you my salary and you can tell us truthfully which of us is richer. But the crypto people have figured out a way to do it without a trusted third party, where they can use something called garbled circuits, or they could use homomorphic encryption or other methods to compute this, just the two of them, such that the only thing you learn about the inputs is what you can infer from the output, but you otherwise don't see the inputs. Okay, that's cool. However, you could learn quite a lot from the output, right? This is something that the crypto people just leave aside. Oh, well, you can't see the inputs. Yeah, but what if the output tells you a whole lot about what the input is? Maybe you don't want to participate in the query. So you could use the knowledge, the belief style policy in this setting, just like we did in the setting I showed before, where each participant could then decide, based on what they think the other participant knows about their secret, whether they should participate or not, or whether they should just say no. Okay, so I'm just going to skip this. So the way that this works, and this is of course more difficult now because when you are making a local decision, you don't have the entire query to look at anymore. You have the query minus the other guy's secret. So you have to somehow be able to make a decision without knowing exactly what the other person's secret could be. So the obvious thing to do would be, is to do this. It's to imagine, well, if the other person's secret is 10 or 11 or 12 or 13 or 14 or 15 or whatever it would be, then the query would be this. And so therefore I can consider each of those possible cases to decide whether or not I should participate. And in fact, all of these possible beliefs, all of these possible cases, we can actually just represent as a probability distribution, right? Where we can say, not only am I going to have a probability distribution for what the adversary thinks about my belief, I'm going to use a probability distribution about what I think about their belief. I'm going to merge the two things together and do the belief tracking to decide what should happen. It turns out that using this approach is going to be very conservative, because it's going to say if there exists a secret that the adversary could have, such that the adversary thinks that there exists a secret that I could have that could violate the policy, then I'm going to say no. So it just turns out you'll say no a lot of the time in this case. So an alternative that will solve this problem is to actually do the belief tracking as part of the SMC. That is, imagine that you have a trusted third party who's going to know what you know and know what the other person knows and know what your secrets are, and then tell you whether answering the question will reveal too much. Okay, and that will all happen inside of this sort of trusted third party as part of the protocol, right? So the whole process that I showed you before of probabilistically executing the program and doing belief revision and everything else, that's going to all happen as part of the SMC, so that you can only ever learn something about the output and not anything about the inputs. So I won't know what the adversary secret is because I won't be able to see it as part of the SMC. Huh. Rogue animations. So it turns out that this is much more permissive than sort of enumerating all of the adversary's possible values. The problem is, I think this is only of theoretical interest, because secure multi-party computation is already literally 1,000 times slower than normal computation. And now we're saying, let's do probabilistic interpretation, which is more than 1,000 times slower than regular interpretation. And let's do it all together in this setting. But on the other hand, it could be that for queries that happen infrequently enough and are of sufficient import, you would still want to do it. Okay, and in that paper, there's an empirical analysis of these two ways of doing things and showing how the precision improvement occurs for the second case and not the first, and so on. Okay, so that's it. So I've talked about knowledge-based security policies and how we can implement them using what we call belief tracking, using abstract interpretation, and performance with intervals seems reasonable, although can always be improved, especially when dealing with this overlap business. And that's it.
Questions?
Yep.
I'm not sure if I got the multi-party thing, but one issue I see where thinking of multi-agent is important is if you talk to k.com and think about whether you should answer the queries, and then you talk to something else.com, you have to somehow think whether there is communication between these guys. And
I think everybody asked me this question, and I realized that the thing that I find amusing about this is that no one thinks that access control has exactly the same policy. So let's imagine we don't use this crazy thing, and we just have access control. And so people say, hey, can I see your data? Yes, you can see my data, I trust you. Well, they could do the same thing. They could take your whole data and ship it off to somebody else. That really the problem is no different in our setting than...
The community side where people could accumulate the knowledge they get from different sources.
No, I know, and they could do that with access control too. So let's say I'm willing to tell you my birthday, and I'm willing to tell Andy my birth year, and we use regular access control policies that make no mention of beliefs. If I presented to you that system, I almost can guarantee you that nobody would ask me the question about collusion. And it's only because we use these brains and we represent what you can infer about things that people think, well, there are other ways that I could infer them, like if I talk to my friends who also talk to you. So it's a fair point. Collusion is important. What I'm saying is that it's no different in our setting than in any system in which you have a security policy that applies to one principal differently than another principal. They can always collude to share information that you didn't want one of them to have about the other.
Maybe this could be addressed somehow by you being partially anonymous to whoever's asking the question. So he doesn't get to ask you as many questions as he wants, because at some point you say, I'm not going to answer any of your questions, but this persona does not exist. You can ask me again randomly without knowing who I was before.
Yeah, so for something like Facebook, where the advertisers really don't care about you personally, yeah, that could work. That's an interesting idea. Yep.
So I thought I was understanding the merging problem, but I'm embarrassed to say that I don't understand it.
Okay.
Because, so in terms of geometry, the convex hull of just a bunch of polygons is going to be their bounding polygon anyway. So,
yes.
so that doesn't matter. So what is exactly that?
It's the precision that matters, right? So if let's say I have 7 polygons and I have to smush them down to 6. Okay? So now what I want to do is I'm going to retain many of these. Well, I have many choices to convert 7 to 6, right? I need to draw a box around some pair of them.
I thought that joining was always converting a bunch of polygons to 1, but that's not true.
No, I wouldn't want to do that, because then I would lose a whole lot of precision,
okay.
Right?
Oh. How do you choose?
It's random.
How many you?
It's whatever order they happen to be in the list that we're maintaining. And you would not want to literally randomize it, I don't think, because the performance is so dramatically, and the precision is so dramatically different that I think it would be very frustrating that if somebody asked you a question, you say no. They could ask, it's like the kid that asks one parent and then asks the other parent, and then you, oh yeah, sure, that's fine. That you really want it to be deterministic, and you just want to make the best choice you can.
So, and Josh, you don't even know how many polygons you should merge to, right? So if you have like 7 polygons, you don't know, should I merge 1 or 2 or 3 or 5?
Yeah, that's right.
Even that choice.
Even that choice
is not clear.
That's right.
So to address the kind of collusion problem, you could just maintain one belief state about what kind of everyone knows about
That's
you,
right.
So
that would be really conservative, right? And again, you could say the same thing with access control. I could have one access control policy for the whole world, which would basically mean I'm going to say nothing to anyone, right? Because I'm not going to tell Facebook the same things I would tell my wife.
Although your system maybe lets you kind of partition up the world slightly more.
Yes.
So you could say there are some people, they might talk to each other, but they're not going to talk to these guys.
So this is a good point. So one thing I hinted at before is that you can maintain a representation of multiple beliefs to hedge your bets against this kind of collusion. And we've just been talking about it, that our abstraction already represents multiple distributions, right? So you could take advantage of that by using our abstraction to represent many distributions that represent the possible beliefs of the adversary with or without collusion, for example. The problem is that while that sounds good, our particular representation is not optimized to do that, and it will be very imprecise. Like we tried to do that with this multi-party stuff, and we just always said no, because the way that we collapsed the distributions turned out to be pathologically bad. But I think that would be a cool angle for future work.
At least it fits your framework.
Yeah, that's right.
I guess you're hitting the notorious problem with access control is that where do you get the policy? And so your particular policy like is probabilities.
Yeah, where does the threshold come from?
Yeah, where would you feel for
So I don't understand privacy policies. So I'll tell you that maybe you guys have used this trick too. The standard trick in computer science research when something boils down to a policy problem is you make a system that allows many possible policies and say, hey, people can encode any policy they want. They can do this policy or this policy or this policy, and they leave aside the question of, well, is that a useful policy? No idea. I have no idea whether it's a useful policy. I don't think anybody knows what a good privacy policy is because I don't think people know what the value of private information is. I mean, people like Facebook, advertisers have some sense of the monetization of your private information. They know how much your social security number is worth, or your birthday, or your gender, or your bank account number, because you can sell those on the black market. But in terms of, for example, the future-proof value of your information, maybe it's not worth anything now, but in 5 years, when they can sequence your genome, that personal information might be very valuable. I don't know. So really, this is just saying we want to not have something that's all or nothing, where it's either you give them everything or you just keep it all to yourself. And so it allows you to hedge your bets and do principle of least privilege a little bit more. But in terms of the exact value at which to set the threshold, I don't know, personal preference. I know that's not very satisfying. I wish I had a better answer.
And then the other notorious problem with like Bayesian reasoning is like, it's where do you get the priors? You know, never ask
Yes, yes. Yeah, so where do you get the prior belief? So when you're doing this Facebook stuff, or when you're an anonymous face in the crowd, you can get demographic information that says the likelihood of you fitting into some sort of mold, and I think that will work. Although, the funny thing is that if this were to take off and become the way to do things, we wouldn't have that information anymore, right? Because people wouldn't be sharing it. So then you really wouldn't be able to determine the priors. But at the moment, I think there are public sources of information you could use for at least some services that would give you a reasonable prior. But if you're worried about interacting with someone who might have auxiliary information about you, it's going to be very hard to estimate what that would be. But assuming that they could know any auxiliary information this is basically what differential privacy does, yields essentially zero utility. I mean, any attempts of applying differential privacy to the sorts of more personal data release situations that I've been talking about gives you zero utility. So that's no good either. So again, hard problem, I'm not sure.
Okay, well, let's thank Mike for a great talk.